Hi everybody, I'm the greatest living inventor, and today we'll talk about my invention that is used to help with the thirst when people don't have water. They use desalination and taking seawater and taking the salt out of the water, so it's fresh water that they can drink. It's called desalination, and but it's very expensive. So my invention is used to make it very cheap. Okay, so the invention is called the Abyss elevator, and you will see why in when I'll show you. Okay, so Abyss elevator. In my book, it's united with another invention, which is the replacement for palm oil. But here I will split them because I tried to record it, and the software said there isn't enough space on the disk, although there is a lot. So I think it doesn't like it when it's over an hour. So I will split it to this invention, and I will talk separately about the palm oil replacement. Okay, so Abyss elevator, and what it is cheap desalination. Okay, what desalination means? This part, it means salt. So de means not. Okay, so it's not salty. So we take water from the sea and we turn it into fresh water. We are taking the salt out of the water. Okay, and now I'll explain how it's done and why it's expensive today, and why my system is cheap. 1 second, I'll take off my shirt. I think it's called hood. Okay, so how is the desalination done? It's done using something that is called reverse osmosis. What is reverse osmosis? First of all, let's see what is osmosis. Osmosis means, for our sake, it's like I'm not explaining theoretical ideas, although it's interesting. It's taking the salty water and pushing them through a membrane. A membrane is a thin, like a plastic bag, okay, and that has a lot of holes in it. Okay, it's like a surface that has many holes, like Swiss cheese, but it's made of plastic or some other material, and this is called membrane. You can think of it as a filter. Okay, and we take salty water. Okay, if we have water, and with salt, and okay, this is supposed to be salt, and we put it through, we put it through this membrane, and when it comes out, we have only water. Let's do it in okay, this is fresh water. Without the salt. And this is salty water. Okay, the idea is very similar to if we take in our kitchen flour. Okay, we have a bag of flour. I don't know how to draw this, but we have flour, which is used to make bread and cakes. Okay, we have flour and we put it through a sieve. Okay, a sieve is like a net. I'm sure you know what it is. Okay, this is a sieve. And it's called to sift. We are sift the flour, and here we have thin flour, like if this was with big chunks, and here it's like only little chunks, only powder. Okay, so this is like a thin powder. Flour with chunks. Okay, so I hope you understand that if we put it through the sieve, it comes out without what we don't want, without the chunks. These are gone. Okay, here it's clean. So again, if we put it here with the salt, we put it through the sieve, like through the filter, through the membrane. And here we have it without the unwanted part, which is without the salt. The salt is gone. Okay, but when we do it like this, it takes a lot of energy. Okay, I'm not going into why. Osmosis is usually putting a liquid through from both sides of a membrane, but the liquid always wants, the water wants to go, the little molecules of the water can pass, and the sediment, like the salt, the thing that is dissolved in the solution, the particles of the salt cannot pass, they are too big to go through the little holes. But usually the water comes in this direction, and we want it to go in this direction. Okay, normally if we don't put energy into the process, the water wants to go and to the high concentration and make it into a low concentration by bringing a lot of water and make the salt more diluted. Never mind why, but that's how it happens naturally. But if we want to do the reverse, this is why it's called reverse osmosis. Osmosis is if we were going in this direction, there, from water into the salt water. But if we want to go back, this is called reverse osmosis. We need to put energy in order to push the salty water through the sieve, through the membrane. Okay? Here it's done by gravity, and but here it needs, in the liquid, it needs a lot of force. Okay? So it needs a lot of pressure, which means a lot of electricity. We use the electricity to push the water in high pressure, the salty water in high pressure, into the here where it's low pressure. Okay, if we want pressure, to use the pressure to push something, on one side we need high pressure, and in the other side we need low pressure. That's what it means to push. Okay, if I'm pushing someone, I'm applying pressure here, and on the other side, if someone applies the same pressure, nothing happens, he will not move. But if here it's low pressure, someone weak, then what I'm pushing will move. So the same is here. We need here high pressure, and here we need low pressure. Let me write it lower. Low pressure. Okay, so again, this requires this arrows requires energy. Okay, this process, I will change the marker because it's not writing very well. Okay, this also doesn't write very well. Sorry, one second. Okay, so it requires a lot of energy. Which means a lot of money. Okay, so many people have the sea, but they don't have rain, and they don't have enough money for the energy to make this process. It needs a lot of electricity to have high pressure here, and the low pressure is no problem because the normal pressure is the low pressure. Here it's low pressure. But to make the high pressure, we need something mechanical, a lot of energy, and which requires a lot of electricity, which means a lot of money, and they don't have it, and they don't have water. Okay, for example, here in Israel, they use desalination, but it costs money. The water costs money. Okay, and I guess in all the world the water costs money because it's, but in places where it's produced in an expensive way, it costs even more, and usually it's where the people are poor and don't have enough. Okay, so how do we solve this? So all this was to explain the problem. This is not the solution, this is still the problem. The problem is it needs a lot of money. How can we make it cheap? Okay, so this is my solution. How to make high pressure and low pressure difference in a very cheap way. Okay, so I'm starting to read for you. I will erase it and do another, draw my solution. So remember, high pressure and low pressure and the membrane between them. We need to go from the high pressure through the membrane, through the sieve, to the low pressure. Okay, so I'm reading, stopping a global thirst and desertification. I will explain it in the another video. I'm splitting this solution into two. By producing desalinated water cheaply, by using the natural pressure of the sea depths to save energy in desalination of reverse osmosis. Okay, I will explain in a moment. Pushing water through a sieve, in quotes. We've seen this, the flour goes through a sieve, so the water went through a membrane, a filter. The water goes through, but the salt cannot pass through the tiny holes. Pushing water requires expensive energy, we've talked about it. We need a lot of pressure, so we need a lot of electricity. So today, desalinated water costs a lot of money. Okay. MacGyver solution, deep sea desalination. MacGyver, when I'm saying MacGyver, I mean he's using what's already there. If you've seen the original series, I saw all the episodes and the first one is the best. He says in the first episode, Pete asks him, it's the first time he meets him, and they ask him what he carries a bag with him for, like what is he going to put in the bag to take with him, and he says, no, I'm not taking anything from here, it's for stuff I will find along the way. Okay, so he improvises with what he has along the way. So the MacGyver part is the part that we use what's already there. So what we use is the high pressure that is already in the depth of the sea, in the abyss. So that's why I'm calling it MacGyver. So MacGyver solution. If you didn't see you didn't watch the series with the something Dean Anderson. I don't remember the name of the actor, but his family name is Dean Anderson. Then you should. It's the original series. You should. It's really good. Okay, so solution, MacGyver solution, Richard Dean Anderson. Deep sea desalination. Okay, I'll write it here, although I need the, no, I need the spacing. So deep sea desalination. So it's the same desalination, but we are doing it in a more, in a cheaper way, less expensive way, much less expensive. Sorry. So down at the bottom of the sea, there is a lot of pressure for free. If we have the sea, and all this is the sea. Okay, sea. And this is the land, and there is like a house here. Okay, so in the sea, like this is the factory, for example, and instead of doing the process here, where we need to make the high pressure ourselves and it costs a lot of money, we make the pressure here where there is high pressure anyway. Okay, high pressure. Okay, here it's low pressure. Why? Because as you know, if you ever went through into the pool, the swimming pool, and tried to dive down to the bottom, like it's 2 meters or something, your ears hurt. Okay, they hurt a lot more than if well, for example, if you were in the airplane very high in the air, and you are landing, the airplane is landing, you have the same pain in your ears. But the airplane is going down a huge distance, and here even a small distance gives you the same pain. So the pressure is much higher, much stronger in the water. Okay, higher it's confusing because the more down you go, the deeper you go, the stronger is the pressure. So I will not try not to say higher. I will try to say like well, these are the terms. So please understand that this is deep down and this is up and close to the surface. But the low and high it means strong and weak. Okay, pressure. I don't want to use completely different terms because it's like these are the normal terms. Pressure is high or low. But deep down in the bottom of the sea, there is high pressure, strong pressure. Okay, so if you ever played, I used to play in the bathtub as a child with an empty glass, okay, like a glass of water, and put it into the upside down state and push it into the water, and experience how it doesn't want to go down, like, you know, because there is air in the there is buoyancy from the air inside. I'm sure you've done it in the bathtub too. So any child does this. So if we do the same thing here, if we make like a tall structure here, that is filled with air, which is hollow, it doesn't have anything inside, it's filled with air, then the same pressure, let's even make the top open. Okay, so the same, and all this is filled with air, just normal air, like you have a big well. Okay, so or like a huge glass, empty glass. So, but it's not made of glass because it needs to withstand a very high pressure here, so it's made of concrete or metal. So, what I'm trying to say, the same pressure that is here and here and here and here is the same pressure that is here. Why? Because it's all air. And the air doesn't have much different. You are right that here it's like a few hundred meters above this, and all this air is pushing down with all its weight, but it's not much weight. Air is not like water. Here it's like low pressure, and here it's like slightly less, but still low pressure. Okay, so all this is the same pressure for us. Okay, so if we, in a naive way, I'm erasing this, you understand all this is the sea. So, if we want to make the desalination, remember pushing the water through the sieve, through the membrane. If we put the sieve in here, between the high and the low, we add high pressure and pushing it to the low pressure. If we push this from the high pressure to the low pressure, through a sieve here, it's not correct. I'm just trying to tell you why it's not correct. Okay, if we add small holes, membrane, and we push this from high to low. Will this work? No. Why? Because the difference between here and here, this is very thin. The membrane is very thin, and if we put here, measure the pressure here and here, above the membrane can be maybe like less than a centimeter in the thickness of this. So a centimeter to here or a centimeter to here, it's almost the same pressure. It's like this and this will be the same pressure, so it doesn't give us the effect of something pushing hard and something not resisting. It just gives us the effect of something pushing and something else pushing back, almost the same. So they equal. They are negating each other. Okay, so this is not the way. Okay, so what is the way? The way is from here, from the high pressure to the low pressure here. Okay, if we had, so now I'm explaining how we are doing this. Okay, this is now the right solution. We take water in a bag. We put it in a bag. And all this is water. Everything is water also here, but here it's a closed bag filled with water. And we drag we close it so the water cannot go out. And we drag the water, the bag with the water, to the abyss, to the place near the bottom of the sea. Okay, so now we have you know what, let me draw it in another way. This is the bag. When it's big, and this is the bag when it's small. Okay, the water is not really compressible, but I just want to emphasize that here all the water from the outside are pushing to the inside, and they are compressing. Here it's high pressure, which means strong pressure, like we said. Okay, so it's the same water, but here it's high pressure. Here it was low pressure because it was near the surface of the water, and here it's high pressure because it's deep down. So without any energy, almost, only the dragging of some robot or something, or a rope to drag it down, we have here high pressurized water without electricity, without any energy. We don't, all this energy is coming from the weight of the water outside the bag, the water of the sea. Okay, so here, this is like, imagine this like a shaft of an elevator. Okay, this is like elevator shaft. Okay, why? Because it's first of all, it's empty. Sorry, it's closed to the outside world, but here inside there is only air, and it's vertical. And you will soon see that we have something that that can go up and down inside. Okay, and also it has a door. This is also crucial, that here in the lower part there is a door. Okay, the door can open. If the door is open, we can bring there, before we open the door, we can attach the bag of water, and before we open the bag of the water, we can put here a new membrane. Okay, this is the filter, the sieve. Okay, so when we open the bag of the water, all this high pressure water that is closed inside the bag is not flexible, and is pushed from all the sides by the water of the sea, and all this water inside the bag, not all the water outside the bag, but all the water inside the bag are squeezed, pushed through the sieve. Okay, with the water of nature. We don't need to pay for the energy. Okay, so if we put here a bucket, okay, this is supposed to be a bucket. It's still it's inside the elevator. I just didn't have room to draw. Then all the water from the from the bag, the salty water will go through the perforated holes, the perforated membrane, and will end up here where it's fresh water. Okay, so now we have fresh water for free here. So now, fresh. Which means without salt. And this was salty. I don't know if you can see the difference in color. I will use another blue. Okay, it looks the same, but this is dark blue and this is light blue. Okay, I don't know if you can see it. This is salty and this is fresh. Okay, so all we need to do is treat this like an elevator or like a well. And okay, now all the water here are squeezed and we have the fresh water in here. So here, like in the Old West or anywhere that there is a well, that you dig down into the ground, deep down to get water and bring it up using a rope and a bucket. So this bucket is connected to a rope that goes all the way up to here, and here you have some wheel, and you roll it up. Okay, you bring it up and you have the water for free, almost for free. It's just the energy of lifting the water here, which is not very much energy. It's much less energy than making the water high pressure. Okay, so I will read it to you now and I hope you will understand. MacGyver solution, deep sea desalination. Down at the bottom of the sea, there is a lot of high pressure for free. Okay, step 1, lower reinforced, which means the walls of the well or the elevator shaft are strong because it needs to withstand a lot of pressure from the outside. So lower reinforced elevator shaft down to sea floor. Step 2, robot attach new filter to door so the water goes through. So we have a robot inside that puts a new, or some mechanism that puts a new filter, a new membrane. And 3, collect water in a bucket and pull it up to the surface. And then go back to step 2. Okay, after this, we don't need to build the elevator again, or the well, like well. Okay, the elevator or the well is already built. We don't need to build it again, only put another filter and then lower the bucket, open the doors, the water come, put another sack here, lower the water, put a new filter, we filled another bucket, we take the bucket home. Okay, so that's it. That's my invention, and I will see you in the next invention. Thank you. Goodbye.